All right, guys, we'll give it just a minute. So you guys say you probably already saw, but I posted your grades for the midterm exam online already. I posted those yesterday, and if you have any questions on how it was graded, it's obviously being graded electronically. So I had to, I tried to write comments in, where I could, or, write things online. You can take a look at that. I'm going to scan in and post the solution set so that you can see, what the correct answers are. We do have another midterm coming up in November. I believe it's November 16th. So it's about, maybe 3 weeks away. So keep that in mind. If you guys did well on the exam, you want to keep your grades up. If you didn't do so great, let's get you prepared for the second midterm so you can bring your grades up. If you want to talk in office hours, we can figure that out too. Let's see, about the project, are we allowed to work up to 2 or 3 people? So you guys are asking about the how many people are allowed in the project group. I mean, it's kind of up to you. If there are 3 people who you really want to work with, I'm okay with that. It's we have a small class, right? And so, I just want to make sure that, we have, enough projects that people are working on. And also, if you have 3 people, we have to make sure that the project is going to be, the workload is going to be spread out, and that the project is going to be sufficiently complex then that each of the 3 people will have, enough work so that they're sharing the load of the work. So I would say, if you want to work with 3, then, why don't you send me an email and then tell me who the 3 people are, and then, make your case for it. I just want to make sure that, that the project has enough in it so that everybody's doing something. Let's see, hang on. Let's bring in, there we go. Anyway, and then don't forget, I think we're coming up on when I need your project descriptions, right? So I'll need to get essentially a page, it's a paragraph, essentially about who you want to work with, and just a couple sentences about a brief description of what you'd like to do for the project. You don't have to scope out the math, you don't have to do anything, just I want to do a project that looks kind of like this. And it's non-binding, right? But it's to get you started thinking about the project, because you basically have a month and a half left, to the semester. We're kind of coming up on maybe a month and 3 weeks or so left of the semester. So it's going to end much more quickly than you think. We don't have a final exam, we just have the project. So keep that in mind. Anyway, with all that said, we're going to start with chapter 2.5 today, which is an interesting concept. So 2.5, and I realized that one of the classwork pages that I posted is actually a duplicate of the other one. So I'm going to take off one of those classwork pages. And I have 2 assignments up for 2.5, 2.6, but I'll take off one of those because it's unfair for you to have to pass the same thing in twice. And then we'll get that taken care of. All right, so 2.5 is called linear isometries. All right, so let's start talking about what is an isometry? Okay, so when we talk about what's an isometry, we're going to say an isometry is a map. So it's some kind of transformation. Right, and remember our map, this some kind of transformation basically is like our matrix, right? That we we take this matrix and we multiply it by our inputs, okay, our X, Y, and Z, or whatever your variables are. And then it basically takes whatever it is that we're trying to transform and it does something to it. So this is a map. So we say it's a map, it's some kind of a transformation, but an isometry is a map that preserves distance, what we call preserves distance. It also preserves the angles. angles as they are, but the distance is easier to show actually. So let me write that down like in math, and then we'll start talking about like what that means. So if I've got some kind of like my map, represent that as A. A is my like transformation map. And A says, I'm going to go from the nth dimension to the nth dimension. So I'm not like changing dimensions at all, right? So I've got some kind of a transformation, and I'm staying in the same dimension that I was before. So when I do the transform on my X inputs, and I do the transform on my Y inputs, and I take the distance between them. So this is our distance formula, right? Right, remember, this is like our basically Pythagorean theorem distance formula. This is like saying, right, this is the transformed is equal to the original. So let's write that down too. So this A of X, so this is our, let me write this. Transformed distances are equal to our original distances. Okay. All right, so that's an isometry, and this is going to be true. So we'll say for all X, Y, and these are all like, you know, real numbers inside of our nth dimension, right? Where n is our first dimension, second dimension, third dimension. We tend to stick to first, second, or third. Second and third dimensions really when we're doing stuff. The math is going to extend out to other dimensions, but it gets harder to visualize. So we stick to the second and the third dimension. Okay, so, right, we say it preserves angles and it preserves distances. Distances are what we're really trying to focus on. As I'm going through, I'm going to go through with our lecture examples so that we'll actually have a good printout of our lecture examples, but let's go through some types of transformations, and we'll do some examples, like specific examples. So when I talk about translation, okay, so translation, and this is the lecture examples for chapter 2.5, by the way, that I put up on our website this weekend. So translation is where I take an object and I move it over and up, or I move it over and down. Say, for example, translation is where we just simply move our shape by a specified amount. Right? So basically, it's kind of like, you can imagine I have a 3, 4, 5 triangle, okay, in my XY plane. And then I'm going to move it like over and up. So I now have, this is my transformed. I still have a 3, 4, 5 triangle. So like all I did was move it, right? So my angles from my original triangle are the same as the angles that I had before. My side, 3, 4, and 5 are the same, 3, 4, and 5. So this is like my x-axis, this is my y-axis. We're actually going to do this here, you'll see. Okay, so let's talk about a translation map. So translation map. So if I say, this is my distance on my translation map. So A is the distance that we're moving things, right? And I'm going to apply it to my X. I'm going to apply it to my Y. So I've got some kind of X vector. I've got some kind of a Y vector that I'm dealing with here. So what I would say is, I'm going to move the X by my A amount. And I'm going to subtract, I'm going to move my Y by my A amount. Okay. So A, right, I've moved this over. Let's write this. I've moved this over by A, right? I've moved it over and up. So A is like how much I'm actually moving it, okay? So now what this is gonna look like is I'm gonna go X plus A minus Y minus A. So I distribute that negative to both. So the A's cancel out, and what I'm left with is X minus Y, right? Which is the same thing as if I were to say, right, what's the distance between X and Y, which is distance between X and Y, my original X and Y. So that's my translation map. Can I go back to the notes for just 30 seconds? Sure. Our notes. Oops. There, how's that? Is that okay? Okay. All right. So this is, I'm putting like lecture notey type things inside of our lecture examples so that we can, when I scan this, and you guys can also have it right there. Okay. So let's do this. We're going to plot the points 3, 2, 1, 1, 3, 1, and form a triangle. All right. So 1, 2, 3, 6. Okay, so I'm going to plot. So I'm going to go over 1, 2, 3, 1, 2. So there's point 3, 2. Here's point 1, 1. And then here's point 3, 1. A really tiny triangle. Okay, so here's my triangle. Okay, based on the points that they tell me to do. Now we're going to translate this triangle over 4 and up 2. So what's that over 4? Means add 4 to every x coordinate, right? Over. And then I should have said move it over right. Let's do that. Let's specify right and up 2. Up 2 means we're going to add 2 to every y coordinate. Okay, so now let's draw this out. So then when I do this transformation, so 3, 2 becomes 3 plus 4 and 2 plus 2, which is equal to 7, 4. So I'm going to go 1, 2, 3, 4, 5, 6. Let's add another marker here. 7. 1, 2, 3, 4. Here's my dot. That's 7, 4. Okay. I'm going to take the next one. 1, 1. So it's going to be 1 plus 4, 1 plus 2. 1 plus 4 is 5. 1 plus 2 is 3. So I'm going to go 1, 2, 3, 4, 5, and then up 1, 2, 3. Okay. So it used to be here and now it's there. This used to be here and now it's there. Last one, 3, 1. So 3 plus 4 and 1 plus 2. So 3 plus 4 is 7. 1 plus 2 is 3. So I'm going to go over 7 and then 1, 2, 3. Okay. So let's check. So I'm going to check the distance on each of these sides, right? So when I check over here, this distance from here to here is 1, 2, right? I'm going, this is 3 minus 1, that gives me 2. So, and then the distance from here to here, right? This is from 1 to 2, this is equal to 1 unit. Okay, I'm counting up the units that I have, right? So, size of original triangle, right? So I'm going to subtract these here. So I'm going to go 3 minus 1 equals 2. And then on the y, this is my x and my y. And this is going to be 2 minus 1 is equal to 1. Okay. Now I can do my Pythagorean theorem on this side. My hypotenuse, right, is equal to 2 plus 1. So this can be 2 squared plus 1 squared equals c squared. A squared plus b squared equals c squared. So this is 4 plus 1 equals c squared. So c is equal to radical 5. Okay, so that's how I get that side. Let's do the same thing for the size of the transformed or translated triangle. Okay, so I'm going to go from here to here. So I'm going to count, right? So this new spot is equal to 7 minus 5, that's equal to 2. This is my x's. 7 minus 5, that's equal to 2. On my y's, right, I'm going 4 minus 3. So this is 4 minus 3, that's equal to 1. This side is equal to 1. Okay, let's do our hypotenuse. We can tell what it's going to be, but let's just do it out. So it's going to be the side 2 squared plus 1 squared equals, we'll call it h squared. So this is going to be 4 plus 1 h squared. H is equal to radical 5. Okay, so we can see, right? We've translated this shape, this triangle, over 4 and up 2, and we have not changed the sides, okay? The side lengths are still the same. So this is an isometry. It's an isometric transformation. So I'm going to conclude. Do it in red. Yes. Distance between points was preserved. Therefore, this is an isometry. Also, all the angles are the same. Okay, once I prove that the sides are the same, the angles are going to be the same too. Okay. I'll let you guys finish that and we'll talk about rotation and reflection. Okay. You guys good with this? Okay. So let's scroll down a little bit. Rotation and reflection. This is technically like lecture notes, but I'm putting them in here so we have them as a copy. Okay, so rotation and reflection. We're going to do actually rotation first, and we'll draw things out. So let's so rotation is going to look like, right, here's my x-axis, here's my y. Let's say I have a triangle. Do a right triangle so it's easy to see, right? So if I do a rotation by a certain angle, right? I'm gonna rotate this by a certain angle. Rotate this by a certain angle. What it's gonna look like is this is a rotation by a certain angle. Now remember, right, we're talking about, is this changing the shape of our triangle? Is it this side here is still going to be the same as that side? This side here is still going to be the same as that side. Our hypotenuse is still going to be the same. Like all I'm doing is I'm taking this and I'm rotating it by a certain degree, okay? So my rotation, let's say we'll do rotation by 90 degrees as an example. So if I go rotation by 90 degrees, and I do that on my X and Y coordinate, what I get are, I get minus Y times X, right? We did this in a previous chapter. We talked about like how we actually get these things here, okay? So we can talk about the distance between 2 points, say for example. Okay, so I'm going to go X and Y, and I'll call it U and V. Okay, so I've got these 2 points, X and Y and U and V, right? This is a U and this is a V. Okay, so what that's going to happen is this. I'm going to go XY minus V. I'm going to do the X's. Y's. Right? And how this is going to look is, this is my distance formula, which is based on my Pythagorean theorem. So it's going to go like this. X minus U squared plus Y minus V squared, square rooted. This is our distance formula. I'll write this down in red. Based on the Pythagorean theorem, right? A squared plus B squared equals C squared, right? We did that before here. A squared plus B squared equals C squared. So this is my A squared, this is my B squared, C squared is my hypotenuse. That's what I'm solving for, okay? So it gives me the distance between these points here. Okay, so this is the distance between 2 points. Now, if I rotate these points, by 90 degrees. Okay, what's going to happen if I rotate these points by 90 degrees? Okay, so if I do rotation by 90 degrees on my X and Y, okay, and I'm doing the distance between the rotation by 90 degrees on my U and my V. And I want to figure out, right, So this is X and Y, this is U and V, and I'm rotating them now. So I'm going to rotate my X and Y. I'm going to rotate my U and my V, and I'm going to see what's the distance between them, right? So now remember, right, how the X and the Y change once we rotate them. Sorry, I can speak this morning. Minus YX minus VU. Okay, this is just following our rotation map. Okay, so I'm going to rotate both X and Y and U and V. And what I get is, I say V minus Y, comma, X minus U, which is, I'm going to write down V minus Y quantity squared plus X minus U quantity squared, square rooted. That's our Pythagorean theorem. All right, so remember we're squaring stuff, right? So I'm looking at the difference between X and U. So X minus U quantity squared is the same thing. Oh, X minus U quantity squared. Okay, or even I can write this as, should this have been, yeah, I did that right. Yes, and then here, V minus Y, okay, it's the same thing as Y minus V squared. Once I square it, I'm basically, even if it was negative, right, when I take that difference, by squaring it, I'm just looking at positive numbers. So here, this is the same thing as what I had before, X minus U squared plus Y minus V squared, square rooted. Therefore, our distance was preserved. That distance is preserved. Therefore, this is isometric. An isometry. Our transformation, our rotation is a isometry. Okay. We can also do this for reflection maps. Okay. So if I were to do this as a reflection, this thing would look like, okay, I would go through the same topic that I did before from my original. Let's write down this is our original. And our rotation is here. That's the rotation map. So I'm using the same graph for different things. So our original is here. If I rotate it, I did out all the math to show you. I could do the same thing between U and V and a reflection. Okay, but we're also going to get that the reflection is an isometry. Yes. Yes, both. Okay. Slide the page over a bit, please. Let's see. Is that okay? Can't tell if you can see it or not. Zoom out just a little bit. How's that? Oops. Yeah, I can see it's going off the page here. Let me see. It's getting stuck. Let's see if I can zoom out just a little bit more. There. That should be good. How's that? Yeah, I have a hard time sometimes seeing what you guys see. Okay. Give you guys a minute to finish writing that down. So we just basically showed it for reals with rotation. The same method for showing it will work with reflection. Remember what changes if I reflect across the y-axis? Just the x becomes negative. If I reflect across the x-axis, just the y becomes negative. Okay, same process that we would go through. You guys need more time to write that down? Okay, so we turn the page. Let's talk about projection map. Okay, is the projection map isometric? Is projection an isometry? So let's think about what that's going to mean. So projection, I'll tell you ahead of time that it is not. No, but let's talk about why. Okay, so if I say, I'm going to look at, so the projection. Okay, I've got this point xy, right? And I want to be able to project it, say, onto, you know, some other something, right? So maybe on the x-axis or some other point or whatever. So, or some other vector, and I want to be able to, oops, close the bracket. I'm looking for subtract projection. Right, so we're going to look again at distance, right? I've got some kind of a shape, right? And I'm going to project that onto something else, okay? So what I'm looking at is, I'm going to say, projection. So we're projecting onto, oops, sorry, projecting onto the x-axis here, right? So that's what that means. I have my x, but my y is equal to 0. So we're projecting onto the x-axis. So I've got x and y minus the projection of u and v. We're projecting those both onto my x-axis. So now I'm going to go x comma 0 minus, oops, u comma 0. That's a u. Make that look even more like a u. U comma 0, right? And what that is I go x minus u comma 0. Right? So what that looks like is x minus u squared plus 0 squared is not equal to xy minus uv, right? Because xy minus uv, imagine, right? My y and my v, where are they now? They're just 0. So this, what I have, is equal to x minus u. This is all going to be equal to x minus u squared plus y minus b squared square rooted, right? So these two things are not equal to each other. So this was my original transformation, right? My original distance, and this is my transformed, my projected distance. So let's write that down. This is my original distance between x, y, and uv. And uv. And this is my projected distance. Right? They're not equal to each other. It did not preserve distance, right? So the projection map. Therefore, it is not isometry. Okay. You'll see it too. You know, when you do a transformation, you'll be able to see if it's an isometry or not. You guys all have this. I'm gonna go back to our notes for a minute. Anybody need more time to write that down? Okay. So let's go back to our notes. So let's talk about things, right? We want to talk about things that are both linear and isometries. Okay, so of the different types of transformations that we were talking about here, our rotation map was both linear and isometric. Okay, and then let's talk about what this means. Okay, so let me do this. We'll call it properties. Okay, so the first one is we have M is our matrix for a linear isometry. And this is in our nth dimension, our n dimension. We would say M transpose times M equals our identity. Okay, if I multiply them together, it's going to give me my identity, where I is our identity matrix. And we're in our nth dimension still. Okay. the columns, and this one is super important, I'll put extra stars on it. The columns of M are, they're two things. One is they are, each column is a unit vector. Boy, is that important, unit vector. So unit vector, remember, means it has a magnitude equal to 1. So let's write down magnitude equal to 1, right? So each column, so I take out, I've got a column, right? And I take all the elements out of that column, I square them, I add them up, I take the square root, the magnitude should be equal to 1, okay? The other thing is, each column is perpendicular, orthogonal, to the other columns. How do I tell if two columns or two vectors are orthogonal? The dot product, and the dot product is equal to 0. Oops, sorry, you can't see what I'm writing. Dot product is equal to 0. So I go column 1. Somebody needs to mute themselves. I'm gonna mute you. Mute. All right, so our dot product is equal to 0. Okay, so this here is how we can tell if we're dealing with, right, a linear isometry or an isometric map. Okay, so there are some proofs and stuff inside your notes, which I'm not going to go through because they're in your notes. Your notes says it really nicely. Okay, so we want to be able to maybe work through some of these things in our lecture examples. Okay, so what I'm going to do is I'm going to take a look at example number 5, and it says, is this transformation map an isometry? So I've got 2, 0, 0, 2. Does this do this transformation on the unit square? We're going to be able to see this in both cases, how it doesn't preserve distance, okay? But what I'm going to do is I'm going to check my columns, right? So each column has to have, each column needs to be a unit vector. So I'm going to check if columns are a unit vector. Okay, so that means I'm going to go my first column, 2, 0. So I'm going to go 2 squared plus 0 squared, add it up, square root it is going to give me 2. Magnitude? No. Magnitude is not equal to 1. Okay, so it's not an isometry. I'm not even going to bother to check the other column, and I'm not going to check to see if their columns are mutually orthogonal. I mean, it's going to look like they're going to be, the dot product will be equal to 0, but it bombed out on the fact that the magnitude wasn't equal to 1. So it's not an isometry. Not isometry. Okay, let's do this transformation on the unit square. So my unit square looks like this. The unit square is typically, it's a 1 unit square. Each side is equal to 1, a length of 1. And it's typically centered at 0, 0 at the origin. So here's 0, 0, 0, 1, 1, 0, and 1, 1. So here's my, let's draw this out. I'll do it in green. So I've got 0, 0. I've got 1, 0. I've got 0, 1. And 1, 1. These are all coordinates, right? So these correspond to the vertices. These are my column vectors for each of my vertices. I'm going to apply this transformation 2, 2, right, to each of these vertices here. So watch what's going to happen. So I'm going to draw out. So I'm going to go 2, 0, 0, 2. And I'm going to apply it to 0, 0. So it's just equal to 0 and 0. So that's equal to 0, 0. So my first coordinate still is at the origin. So I'm going to apply this to my next point, 1, 0. So 1, 0 means I've gone over 1 in the x direction and up 0 in the y. So 2 times 1 is equal to 2, 0, 0, 0. So that's equal to 2, 0. So this point here became 2, 0. I'm going to apply this to 0, 1. So that's this point right here, 0, 1. I've gone over 0 in the x and up 1 in the y. So 2 times 0, 0 times 1. So that's a 0. 2 times, I'm sorry, 0 and 2. So then I've gone up here. Okay. 2, 0, 0, 2. I'm going to apply this to the last one, the last point. So this is going to be 2 plus 0, 0 plus 2. Okay, so I'm going over 2, 2. So my transformed unit square, right? What I've done is I've taken a square that had an area equal to 1. It was 1 unit on one side, 1 unit on the other, 1 to 1. And I've now gone, this distance is 2, this distance is 2. Right? So we didn't preserve distance at all, right? Because look at what we did. We scaled it, we blew it up, right? We can show, right, that it's not an isometry, okay? Because, okay, right, our columns do not have a magnitude equal to 1, but also just looking at it, I can see that my transformation did not preserve distance. It actually expanded the distance, right? I've gone from this unit is equal to 1 to equal to 2. So automatically I know that it's not an isometry because it didn't preserve distance. Okay. Let's check some others. All right. So now I want to be able to do this one. So what I'm going to do is I'm going to get my calculator. All right. So now we want to check to see, is this transformation an isometry? So I'm going to look at here. So I need to go. I have to check my column vectors. Check. Columns are magnitude equal to 1, right? They have to be unit vectors, okay? So that means I'm going to go 0.8192 squared plus 0.5736 squared. I'm going to add them up, square root it. Let's see what we get. So I'm going to go 0.8192 squared. Plus 0.57336 squared. Add it up. Raise it to take a square root of it. I rounded it, right? This is where we're getting all these little dregs. It's because this is actually sine and cosine. I'm going to say what that is in a minute. So this is equal to 1. Okay. We're getting little bits left over because of my rounding errors. So that's column 1. Let's check column 2. Oh, column 2 is going to be the same thing, but let's just go ahead and do it. So here's column 1. Here's column 2. So I'm going to go minus 0.5736 squared plus 0.8192 squared, add it together, take the square root. Watch what I do. When I do the minus, okay, watch what I'm going to do. I'm going to go minus 0.5736, and then I'm going to square it on the outside. See how I put it in parentheses? So when it squares it, right, it'll be positive. Okay, when I do that, minus 0.5736 squared. Right, so it's a positive number. If I don't put the parentheses there, I'm going to get a negative number, which would be wrong. Plus 0.8192 squared. So again, we're looking at square root of 1 is equal to 1. So check. So the rows are unit, I'm sorry, the columns are unit vectors. Now I have to check to see if, check if column 1 is perpendicular to column 2. It's only a 2 by 2. I only have 2 columns. So I only have to check these 2 columns, right? If I had a 3 by 3 matrix, right, then I'd have to check column 1 against column 2, column 1 against column 3, but I only have 2. So what I need to do is I'm going to go dot product 0.8192, 0.5736 dot minus 0.57, that's a minus 5736, comma, I'm running out of space, sorry. 0.8192. I'm going to dot product these two together. So I'm going to get 0.8192 times a minus 0.5736, right? x's plus the y's, 0.5736 times 0.8192. I don't even have to do the math out because I can see this is going to be a negative product. That's a positive product, and that's equal to 0. So I did the dot product. The dot product was equal to 0. Dot product's equal to 0 when I have a right triangle. Okay, which means that these two are orthogonal. They're normal to each other. How did I do the orange part again? Orange part. Oh, I mean for this example right here. So what I'm doing is I'm transforming our unit square. The unit square has coordinates starting at the origin and 1 unit in each direction. It's like how we define our unit square. So I've got a coordinate at 0, 0. I've got a coordinate at 1, 0. I have a coordinate at 1, 1. And I have a coordinate at 0, 1. I'm going to apply this transformation to each of my 4 corners, okay? Each of my XY coordinates to get a new transformed coordinate. So I take my matrix and I multiply it by 0, 0, right? So each coordinate becomes a column vector. So remember, I go first row times first column. 2 times 0 plus 0 times 0 gives me 0. Then second row, first column. So I'm going to go 0 times 0 plus 2 times 0 gives me 0, 0. And I do that over and over for these 4 coordinates. And that's how I get the coordinates for the transformed square. Right? The square has been multiplied by 2 in the x direction and multiplied by 2 in the y direction. Okay, so we've basically changed, right, our area from area equals 1 to area equals 2 squared. Okay. Okay, so is it an isometry? Yes, because the columns are unit vectors and each column is perpendicular to the other columns. So yes. Okay, this one here. This is actually, I'll tell you what this is, example 6. This is actually, I'll write it down in a different color. You didn't know it because I did it offline, but this is a rotation by 35 degrees. Okay, so rotation by 35 degrees says cosine of 35 degrees, sine of 35 degrees, minus sine of 35, cosine of 35. Right, I did it offline. I wanted to show it to you first. So if I go cosine of 35, right, so cosine of 35 degrees gives me 0.819, and I rounded up to 8192. That's why we have a little bit left over when we do stuff because of the rounding errors. So we already said before that rotation by an angle, right, any angle, was an isometric property. Okay, it was an isometric transformation, and we just did it. Okay, let's do it again on this one here, example number 7. Okay, so example number 7. So is this an isometry? So 1, we're going to check columns are a unit vector. That means is the magnitude equal to 1? So I'm going to check this column first. So this is going to be 0.9537 plus 0.3007 squared. Add it up, take the square root, and let's see what we get. So I'm going to go 0.9537 squared plus 0.3007 squared. Okay, so again, I've got a little bit of rounding error because you'll find out later this is a cosine thing. So 0.9537 quantity squared plus 0.3007 quantity squared, I get 0.99996, and I take the square root of that, and I get essentially that's equal to 1. I have some rounding errors because I scaled. Okay, so good. So that column 1, this is column 1, do column 2. Okay, so I'm going to check this right here. Minus 0.3007 squared plus 0.9537 squared. They're the same numbers essentially, right? Because when I square a negative number, it's the same thing as when I square the positive aspect of that number. So I know that's also going to be there. So that's good. So each column is a unit vector. Yes. Let's check if column 1 is perpendicular to column 2. Okay, we're going to do the dot product. product equals 0. I'll put a question mark. Okay, so column 1. So I'm going to say 0.9537 comma 0.3007 dot with minus 0.3007. Oops, sorry. Close my parentheses too early. Comma 0.9537. There. Okay, so let's go ahead and do our dot product. So what that's going to look like is 0.9537 times minus 0.3007 plus, right, our x's times our x's plus our y's times our y's. Now I can see it already, right? Same product, but this one's negative and that one's positive, and that's equal to 0. So yes, they are orthogonal to each other because the dot product is equal to 0. So I'll say yes. This matrix, this transformation matrix represents an isometric transformation. Okay, I'll tell you what this is. You didn't know it. This is a reflection by theta divided by 2. Okay, so that means I did cosine of 35 over 2, sine of 35 over 2, minus the sine of 35 over 2, cosine of 35 over 2. So I reflected, right, over that angle here. Okay, so reflection is an isometric transformation. Rotation is an isometric transformation because the columns are unit vectors and the columns are perpendicular to each other. We call it mutually perpendicular. Okay. I'll let you guys finish writing that down. Let's try. We're going to check these other ones here. So example 8, let me scroll up a little bit. Is this transformation an isometry? Okay, let's take a look. So let's see. So I have to do the columns. I have to do, my first check is going to be, are the columns unit vectors? Unit vectors? Put a question mark. Okay, so let's check it out. So minus 1/2 squared plus minus radical 3 over 2 squared square rooted. So what this looks like is 1/4 plus 3/4 square rooted. So that's 4/4 square rooted is equal to 1. Okay, so column 1 is good. Let's do column 2. So column 2 has the same numbers. All right, so minus radical 3 over 2 squared plus 1/2 squared is equal to 3 over 4 plus 1 over 4, which is equal to 1. Good. So column 1 and column 2, sorry, that should be square rooted. Column 1 and column 2 are both unit vectors, right? Their magnitude is each equal to 1. Let's check to see if each column is perpendicular. So column 1 perpendicular to column 2, that would be our dot product. So I'm going to go column 1 dot column 2, and that should be equal to 0. And I'll put a question mark, so we don't know yet, right? So let's write it out. So this is going to look like minus 1/2 comma minus radical 3 over 2 dot minus radical 3 over 2 1/2. Okay, x's minus 1/2 minus radical 3 over 2 plus our y's minus radical 3 over 2 times 1/2. Okay, so this is going to be positive radical 3 over 4 plus, oh, it's a negative radical 3 over 4, which is equal to 0. Check. Yes. Okay, it satisfies both. Okay, each column is a unit vector and each column is perpendicular to the other column. Okay, this one here you didn't know it, but I'll tell you. This one here is reflection in the line that makes an angle of 60 degrees with x-axis. We'd say reflection. That's where I got these numbers from. Okay. Let's do it with a 3 by 3 now. Okay, so the same thing, I have to check now 3 columns. Okay, so I have to check the first column. So 1, we have to check for unit vectors. Okay, so column 1. So I'm going to go like this. 1/3 squared plus 2/3 squared plus minus 1/3 squared. Okay. So this is going to be 1/9 plus 4/9 plus 1/9. Why is it not adding up? Oops. Oh, this is a typo. I'm sorry, this is a typo. This should be a 2. I was like, that should be adding up. I'm sorry, folks, that's a typo right there. That should be a 2, which would make this a 4. Okay, so that's 8 plus 1 is 9. This is 9/9, which is equal to 1. So column 1 is good. Let me just check to see. 2/3, 2/3, 1/3, 2/3, 1/3, 2. Okay, good. So it's just this one is a typo. So that's a 2. Column 2. Let's do the same thing, same numbers, right? So this is going to be minus 2/3 squared plus 2/3 squared plus 1/3 squared. Okay, so this is going to look like 4/9 plus 4/9 plus 1/9, which is equal to 1. So column 2 checks out. Column 3 is going to look like same numbers. So 2/3 squared plus 1/3 squared plus 2/3 squared square rooted, and that's equal to 1. So column 3 checks out. So unit vectors, they're all unit vectors. Okay, I'm just going to do, we have to check, the next one is column 1 perpendicular to column 2, and then column 1 perpendicular to column 3. Because we have to check that these are orthogonal and these are orthogonal, and then I have to check column 2 perpendicular to column 3. Okay, we would be doing dot products for all of these. Okay, they're all similar numbers here, so you can see, right, if I go 1/3 times a minus 2/3 plus 2/3 times 2/3 plus a minus 2/3 times 1/3. Okay, so when I do this on here, what I'm getting is these are all dot products equal to 0. So I'm not going to actually work through the dot products, but all the dot products are equal to 0. So yes, this is all true. I'll let you guys work on those offline. Okay, which means therefore, yes, this is isometry. It represents an isometry. Okay. All right. Do you remember this one, example 10? This one from last time we did this. This was our projection matrix. So let's just show you a counter example. We've already said projections, not isometric transformation, but let's just go ahead and do it. So I have to check for unit vectors, which means I need to distribute my 5 into all of these here. So this is going to be 1/5 and 2/5, right? So column 1 is going to look like 1/5 squared plus, it's a 0 squared, plus 2/5 squared, square rooted. So this is 1/25 plus 4/25, which is 5/25, 25ths, right? Which is radical 5 over 5, which is not equal to 1. Oh, it bombed out already. I don't have to check anything more. It already failed. It's not, my first column is not a unit vector. I don't care if the other columns are unit vectors or if I can take the dot product and find out that they're mutually orthogonal. It doesn't matter because it's already failed. Therefore, no, not isometry. This is our projection map. When we mapped, when we projected onto a plane. Okay. All right. I think what I'd like to do, this is an important concept, this handedness concept. And I'd like to actually pick that up next time. We're getting close to the end of our class period, and I want to finish this handedness discussion next time. We have plenty of time this week because we allocated all day Thursday to be like a practice time, although we can leave early on Thursday because you guys also have a quiz on Thursday, I believe. Is the quiz on Thursday or is it on Monday? I can't remember. I'll need to look. Check your syllabus. I think we have a quiz coming up on 2.3 and 2.4. Okay, so keep that in mind. But this, right? Okay, so handedness, I want to be able to talk about and what it means. Okay, so we're going to come back to this topic on Wednesday. Okay, guys? And we'll go through some classwork problems on Wednesday too. Okay, you guys have a great day.
Thank you.
Bye. Take care.
Oh, would you mind going over the classwork for 2.4, question 4, please?
Yes, if it's quick, because let me see, give me just a second to get out my stuff so I can see. Is that, is that this one?
Yeah.
Yeah, let me just talk it through because it's actually a long example. So we've got a circle, right? And I can extract where my center is and what the radius is from the equation, right? So my center is at -3, +2, and my radius is equal to 2, which means I can plot it. So I'm going to go over 3 and up 2, and I'm going to go over 2 in every direction and just kind of sketch it out, right? We want to be able to reflect it across the line y = 3x, which means I have to figure out what angle that is, right? So I kind of did a little zoom up, right? So I zoomed up. So I've gone over 1, I've gone up 3. So my tangent of theta is equal to opposite over adjacent, so 3 over 1. So my angle is equal to 71.5. So what I'm doing is I'm reflecting the circle over a line that makes an angle of 71.5 degrees with the x-axis, right? Mm-hmm. So our reflection, okay, is cosine of 2 theta, sine of 2 theta, sine of 2 theta minus, we did this before, right? So I'm going to plug in, my angle is 71.5. I'm going to plug that in, cosine of 2 times 71.5. So I come up with a matrix, okay, for being able to transform my circle. And this matrix is related to this line here because I'm going to reflect across that line, right? And I want a matrix transformation that relates to that line because maybe I want other circles to, you know, reflect across that line, or I want other shapes to, or other things to reflect across that line. So I want something that relates just to that line. Now, when I have a circle, the whole idea and what we're trying to do is to distill down our shapes into the most important pieces. So I don't have to like, oops, sorry. I don't have to, you know, basically reflect all the points on the circle. The only thing I have to do is take my center, reflect the center, and then build the circle back again, right? Because I'll have an algorithm, a subroutine that prints out a circle on the screen, okay? And so that circle, I can send it a center and a radius and it'll print it out. So all I need to do is figure out what's the reflected center. So I'm going to take my center, which is -3, 2. I'm going to transform it. I'm going to reflect it across this line, right? So remember how we came up with that matrix for reflecting across the line. Mm-hmm. So I'm applying it to our point. So I'm going to go first row, first column gives me this coordinate. Second row, first column gives me that coordinate. This is the new center coordinate for our circle, our reflected circle. So 3.5 minus 0.2, and it still has the same radius. So here's my reflected circle. And I like to print, you know, plot these out. You're never judged on your printouts because but it'll give you like a way to visualize. Are you in the right ballpark? I mean, like imagine if we did this transformation, I got something way up over here, and then I know that either my mistake was in the transformation map or my mistake was in the matrix multiplication, right? So I have my new center point, and now I can just redraw the circle from there.
Yeah, thank you for that.
Sure, no problem. Mm-hmm. Okay, guys.
Yep.
I'll
see you on Wednesday.
See you Wednesday. Take care. Bye.
Thank you.